Hello, everybody. Welcome back. It's been a while. It's been a while. We're talking this time about community structures as promised. It's been about a month since the last video. Although if somebody comes along a couple months from now, all these videos are just next to each other. But just know in the lore of this series, it's been a month. And now we're looking at community structures. This is kind of exciting. This is one of the big takeaways, I think, of the entire series. It's kind of building up to this lecture, tutorial, video, showcase. I don't know what to really call it. But code is in the description as always. Feel free to go on GitHub and copy and paste this. I will say that this video is probably a little bit of an overkill on community structures. We go through a lot of different ways to kind of get the same answer. But I think it's good to be thorough, and then that way all the information's in one place. So just know that you can take like 3 lines of code from this and probably be good to go in like 90% of situations that you're going to face. But knowing some of the mathematical insights and some of the background knowledge of community detection is important because this is an ever-expanding area, especially with machine learning still advancing and being included in business intelligence. I feel like this stuff is only going to improve. So, yeah. So let's, is there anything else to say? No, I feel like that's good. Let's transition over to R. And so we're looking at community structures, assortativity, and we're going to be going through the Zachary's Karate Club data again. You do remember Zachary's Karate Club, right? It's like the most important data set ever. But in this one, and I'll save the big reveal for the end, but remember that in this data set, we did have a faction. So the lore of this data set is that there are 2 factions at a karate club, and they're in competition with one another, and they each have their own independent leaders. And so this data already has 2 communities in it. There's 2 factions, and we know the reality of the situation, as it were. So we'll bring that back later. So let's just pretend like we don't have that data for now. We don't know these factions. Well, would it be possible to, without us knowing the faction at all, to be able to find those communities mathematically? So just with the plotting of our network. And that's the kind of challenge today. So what I'm doing here is I'm loading up a couple different packages. We're going back into iGraph. We'll use this ape package later on. It's really good for making dendrograms, and you'll see this sometimes in machine learning. And then this matrix package is just giving us an image function, which I don't even know if I use or not. But there are a lot of notes in this script, so just know that if I'm going a little bit too fast, well, you can rewatch the video, or you can just open up the R script that I have on GitHub and pour through all the notes. I also have like a bunch of references and stuff in here. And so sorry if I don't mention anything that's in the notes, or if I skim over something. This code is extremely well commented, almost over commented, because like 90% of this is just comments. But yeah, so let's get started. We loaded up the karate data which is native in iGraph, or maybe it's iGraph data. And so if we just run the summary of karate, we can see again that this is a network that has weights to it, and we have a bunch of different variables in here. But we're not going to be really using a lot of them. If we lay out, or if we just plot this, we can see that these are the this is the network here with the coordinates generated for us with this function called layout with fr. So all of the plots should have a similar layout, given that we've forced it with this fr lay. So we'll see fr lay later on, pretty much through all of these, layout fra and then layout fra. So that's what all of this is that the object fra is just forcing the network to fit a particular graphing element. There isn't any math behind that. This is just forcing it into one location. So that way we can compare the network as we go along. I'll make this just a little bit bigger, just to see things. There we go. And my camera is covering up the global elements behind me, but just know that there's no tricks back here. Yeah, so let's get started. Components. So a component of a network is not individuals. So an individual could be considered one component, but if somebody's completely isolated from the network, like we saw with the high school data before, they are their own component, but this network is one component. So there's one interconnected graph element here, which makes one component. And so this is kind of the first way of thinking of communities. The fact that all of these are interconnected within the same network generally means that they're a community. In this case, it's a community of people that are interested in karate such that they would be a part of this data collection. So this is like the most meta level way of analyzing your information, but it's useful to think about, especially as you go into things like physics or like sort of larger socio-political comparisons, that sometimes people aren't even in the same network to be considered. So if you have a completely severed network, some of these community detection things are not going to be helpful because they aren't in the same network. So our scope today is just looking at intra-network, intra-component network community detection. So another way to peel this out is through cores. So somebody could be very, very loosely connected. Like if I showed up to the karate club one time and happened to be associated with this data set, and I knew my one friend but never showed up again, I would have a core of one. And so we slowly peel off these cores, like the outer layer of an onion, perhaps. We peel off these layers until we get to a really sort of core element of the data set. And we can plot this with so we have the coreness command through iGraph. If we run this, we can see the coreness level of every actor within our data set at the bottom of the console there. I'm going to assign a rainbow color to each of these cores and then plot it. So if I do this, we can see that people with a coreness of 1, like the person that shows up one time and just has a friend, so me, I'm probably 12, and then I know I never show up again. So I'm the first layer that's peeled off. And then beyond that, we have coreness level 2, which are even more loosely connected. Coreness level 3 is seemingly the same as coreness level 4, but they're even more loosely connected in that they aren't interconnected with the main central nodes here. So remove them, and then we have the core individuals at coreness level 4. And your network can have a ton of cores depending on how big it is. This is kind of why I chose to do the karate data set. It's pretty simple for looking at some of this stuff. But this is another way to think about communities. Is it really fair to call 12 a part of other communities if it's just a coreness level 1 and is immediately removed? Maybe not. Some of the community detection algorithms that we're going to be going through are going to consider 12 as a part of a community. But if you look at coreness, maybe, maybe we consider that like a loose member of that community that it suggests. Moving on, we are looking at clicks next. And so clicks are the maximally connected subgraphs. And so I have an image. Let me pull it up. I pulled up in advance. So this is kind of what we're talking about. A click is basically the maximum group located near where the node is. So here we got this triad here. We actually have, 4 triads. It's like those puzzles you see on Facebook every now and again. It's like count the number of triangles. Yeah, we got 4 triads here. Hope I'm not wrong on that. And this would consolidate a click. And then here we have other clicks, and then on the far right, where my camera's slightly covering up, we had a couple more. So we can do this as well with the karate data set. And in the bottom of the console, we got a table of the different clicks, and we can see what these clicks are. So they tend to be based around Mr. High. So that's just another way of detecting community sizes. I have a little bit more notes on this in the document if you need. But now we're moving on to really the big community detection functions that are provided to us through iGraph. And so everything before this, like calculating clicks, calculating the number of cores, the components, this is sort of what you would do every single time you got a network, is you would go through some of these descriptive statistics of the network and just sort of pull out what the network is actually about. Maybe identify the largest component that you really care about, maybe look at the different cores to see who's loosely connected or fully connected, and then define what fully connected means for your audience, which is an interesting problem in of itself. It may require a literature review or some sort of qualitative insights into the community or the network as well. And then you would do clicks as well, just to see if there are any easy pick-me-ups on people interconnected with one another. And so, yeah. And then the last thing I'll note here is that you can define what a click means a little bit differently. And so here in the clicks function, I put it as the minimum of 3 connections. But you can spread that out depending on your data set, depending on the information that you're walking into your network with. Context really matters and stuff like this. So great, community detection. And this is the big thing. There are a ton of ways to calculate community detection. There's probably like a million. So many mathematicians, so many physicists, social scientists ranging from sociology to political science to communication studies have all come across and identified what a community is slightly differently. And sometimes a calculation will be given, but it'll be a little bit unoptimized, or it won't really like consider the grander idea, or and so people have customized these ever so slightly over time, and they continue to be developed. And if you wanted to publish a paper, you could create your own way of detecting communities and publish that. But I guess like the overall advice would be that you can do this multiple different ways. You're not really hurting anything. Go with theory first, and then ultimately at the end of the day, if you're writing a scientific paper or research or presenting results to somebody, present every single way in which you did it. And odds are that at the end of the day, they aren't going to range too crazily to where you're going to have a massively different result. And if you do, then the math starts to become more relevant as to why you got a different result. So I'm going to give you a very top-down level definition of what each of these community detection algorithms are doing. And then we'll look at the dendrogram as well as the plot, mostly the plot, but I'll go into what dendrograms are in a second. And then, yeah, but just know that this is super surface level. This isn't a 2-hour video going into the mathematics behind each of these. I'll just kind of give like what you might use it for and what like the general theory was when creating the community detection function. So with that said, let's start with edge betweenness. And so edge betweenness is calculating the betweenness of an edge. And we went over betweenness in the past. Feel free to go back to that video if you missed it. But in the past, we looked at betweenness and in the centrality section. And what this is going to do is for each edge, it's going to calculate that betweenness and then remove the edge that has the highest value of betweenness. And then it will, after removing it, it's going to calculate betweenness again and then remove the edge with the highest betweenness. And it'll keep doing this over and over again until eventually you have your communities. So let's look at the function for this. So essentially what we've done is we run, for pretty much each of these, we run the function with our data set first. Usually functions in R require you to put your data up front. And so we ran that. And then we selected our weights as 1 over the edge of karate, the karate weight data set. And so this is the weighted edges in the denominator of the weights for this function, which it requires. And so let's look at the dendrogram first. And so it's a little bit small on the screen, but essentially it's these graphs, you've probably seen them before, where it's like a family tree where it starts off with 2 communities, and then basically it says, okay, well, if you really wanted to press me for more communities, we can go to this level. And then we can go to this level, and as we move to the right, we get more and more communities. But essentially it's arguing for 2. And then these are the actors that make up the 2 communities at the end of the day, colored slightly differently. And as it turns out, these are the factions that we had in our data set, which is amazing. So we can compare this to our faction data to get a real answer, but we'll do that at the end with all of the different community detection methods. And so here, using edge betweenness, probably one of the most common and simple ways of calculating communities, we were able to identify the factions that existed in the data set. Next up, we have fast greedy. So this is going to be similar to modularity, if you hear that. So I think I covered that in a previous video. I'm not sure, though. So when we measured assortativity before, we could use this in the same sort of way as edge betweenness, where we calculate assortativity scores. And then we do this between all nodes until ultimately we end up with a fast greedy way of calculating communities. The way it's called fast greedy is because it was intended to be a really fast way of calculating communities. And sometimes when you have network data that's really, really large, this is the most efficient way to pull out those communities. And then you can decide from there where you want to bring your analysis. So it's a useful tool for a particular case. And so cluster fast greedy is our function here. Here we're just adding the edge weights. We're not adding the calculation we did before, where it's 1 divided by the weights. And then our dendrogram is suggesting 3 communities this time. So this time it's saying we have community here, which was all of Mr. A's karate faction. And then we have Mr. High. And then, and remember that the coordinates was really low. It was a coordinates of 1 on 12, but it's actually included in the community, which is kind of interesting. And then it's also suggesting this other community that isn't really connected in with other members. Note that this community here is completely severed from all the other Mr. High's faction. So it is deciding to make this a 3rd community, although it's pretty close and there's some overlap in here as well. So that's kind of an interesting insight to bring out, is to identify and maybe talk with your business leaders or whomever you're presenting this information to, that there could be an argument for a 3rd community in your data set if you see something like this. Walk trap is our next one. So this one's probably my favorite. And so imagine doing a random walk of your network where you are just stumbling from place to place. And there's actually a really interesting book on something like this. I wasn't planning this, sorry. But there's a book called by Leonard Mlodinow. It's called The Drunkard's Walk and How Randomness Rules Our Life. Interesting book. But essentially, this is simulating randomness where you would walk around this network, and then because of how your network is structured, odds are that you're going to be walking within the same community more times than not. So if you're walking around, let's just take this graph, for example. If you start at 25, what are the odds that just by like the Plinko machine that you're going to end up on a 12? Very, very low. But if you start at 25 and you do a random walk, what's the odds of you ending up to Mr. A, your central node, your karate club faction leader? That's pretty high. So if you do so many of these random walks and then ultimately calculate what shakes out from that, odds are we could call that a community. And so the reason why I like this one is because it's very hands-off. And so basically what you're arguing here is, I don't know if it fits the definition of this, but it's kind of like unsupervised machine learning, where basically you're saying, hey, I'm going to let randomness decide what these communities are, and I'm not going to add a lot of like insights or suggestions to it. And so essentially, it's just randomness walks through these networks, and here it found 4 different communities, which is kind of funny. I started with 25, and that ended up being its own community. You can run this multiple times, and you might be able to get different results. But with the network size this small, it's pretty unlikely. So you may want to set a seed, or like bootstrap this, or run it like 10 times and take the average or something. But yeah, so those are kind of the big ones. There are a couple other newer ones I know less about, but I've included them and their functions here, along with whatever notes I could pull together on them. So Luvian is a multi-level way of calculating community detection, where essentially the origin story of this one was that it was meant to optimize the modularity detection that we used earlier. And so I have some notes on that, but if we run it, we see it also finds 4 different communities. And if we run the modularity one again, where's that one at? Here we go. We found that the modularity one had only 3. So this one clearly added some enhancements to be able to, well, we don't know if it's an enhancement or not just yet, to create a different community, basically. Infomap is another one, which is an improvement upon the walk trap. And so this one draws from information theory, but I couldn't find a lot on it. But if we run this one, we find 3 communities, whereas the random walk one gave us 4. And then spin glass is one based out of physics. And spin glass is like this physics phenomenon about spinning glass and magnetization. And so this is meant to sort of simulate findings in physics to create networks. Way over my head, but we have that function here as well. It finds 4 communities. So we used so many different ways of detecting communities, and at this point in the video, you may just be like, all right, well, listen, I'm just going to pick one of these. I'm going to move on with my life, and you know what? I like walk trap. That makes the most sense to me. I'm just going to use that and argue that everybody should use it. That's great and all, but let's pump the brakes for a second. What we can do is decide to use all of these, and then what we can do at the very bottom, so we can look at the modularity and sortativity again. But, and I'm skipping a lot of notes here, but what we can do is we can compare what finding we had in the function we used versus the actual faction. And so, again, if you don't have this data in your data set, then you're just out of luck here. But in this data set, we have some sort of truth, which is that in the karate data set, we have 2 factions, as I mentioned before. But in your data set, maybe there's different races of people sitting at lunch together, and very few people are sitting at lunch across racial lines. Or maybe it's segregation based on gender or sex, or something else entirely. And so here what you would do is you would plug in those interesting variables, and you compare the community detections that you found compared to those measurable findings within your network data. So what we did was we compared the faction that we know is the communities to what we found in each of the calculations. And I'm sorry, the object that we named each of these are not intuitive at all. I didn't have the energy to go through and rename them all. But spin glass is SG, for example, and so on. So here we take the faction compared to what we found in our function, and then we're comparing it with method NMI, which I put a note here as normalized mutual information. So a 1 means that it's a perfect match, that if you completely lay them over top of each other, it's the same thing. And 0 is that it is shockingly exactly different, which would be almost impossible. I think even randomness would get you closer. So if we run each of these, I put the numbers already here, but they're also down at the bottom. If we run each of these, we see that our edge between us actually did the best. just barely beating out IM, which I forgot what IM is. Our Infomap one. So here we can say, at the end of the day, when we compare it to our faction, we think that there's two communities, and because it's an 83% when we did it that way. What the difference is between those is that, let's just go back to edge between this for a second. If you compare faction to this, I think 9 and 3 are actually in Mr. A's faction. So there's like a little bit of error there. But that in between is that uncertainty between our calculation and what's reported as the faction is actually pretty fascinating, right? Does it mean that somebody lied on their survey on what faction they're in? Or does it mean that somebody misrepresented the truth in their survey, or that they weren't sure? And so you can kind of create like an uncertainty principle about some of the nodes within your data set if they don't necessarily match what these algorithms are suggesting the community should be. And so just something to consider. Probably don't jump to conclusions, but I think that that's just kind of an interesting insight into these networks. And so at this one, I took some of these and posted them as a table, so you can also report them that way. And so, yeah. I have a couple different ways of comparing these results to our betweenness calculation. And then at the bottom, the last section of our slide here is going over stochastic block models. Stochastic just means randomness for our purposes here. But essentially, this is going to create a model to calculate the probability of ties within a group. And then and then make the groups based upon those probabilities. So this code here, we're moving away from iGraph. I detach it here, and we're moving into different packages, intergraph SNA. And so the functions are going to swap out, but some of them are doing the exact same thing as we did before. Block model is the big function that we would use to calculate these probabilities in our model. And then also you can use this package to customize a model. So you can insert your own sort of GLM into this framework and then calculate the likelihood of communities in your own sort of mathematical sense if you wish. But I ran through this and we found pretty much the same result after comparing it to our factions. So there are a lot more notes on how to do this here as well. But that's essentially it. So just to review everything, I'll go back full screen. Hold on. So what we did, that was a lot. My mouth is really dry. I did that all in one take. But what we did at the end of the day was we loaded up some karate data, and then we wanted to see if we could detect communities within the karate data that were similar enough to our factions. You got a lot of really interesting insights about what do we do when it isn't a perfect match, or what do these different calculations really tell us or really supply to us. I know I skated over a lot of the calculations, but it's just because I don't know enough, and frankly I don't know if anybody does other than the authors of some of these calculations. But these are all the different ways where you can do fast and ready community detection in R. I would recommend at the end of the day, run all of them, compare them to different variables you have, and then generate insights from your communities from there. I think if you need to go any deeper into the calculations and precisely how something is calculated, then you can do that for your own particular method that you think is best after doing that sort of fast and ready analysis. So that's going to cover community detection. Next time, we're looking at models. So we're finally getting into some of the statistics and insights that we can do with models. And it's something to think about before the next video, because it'll probably be another month before I upload one, let's be honest, is to just think about what you would do if you had a network and compare it with a completely random one. And then also, what would you do with a network and be able to predict how it's going to change in the future based upon what information you're seeing and how your network compares with others in your field. So if you're DGP is, or if your data generating process is a coffee shop and you have regular visitors to the coffee shop and maybe it's like a bipartite thing, you can compare that to other companies or other coffee shops around the area and generate insights sort of qualitatively. That's one of the really nice things I like about network analysis, is that it works really well alongside qualitative information and sort of paints the truth a little bit more clearly than some of the other methods that I think, through probably no fault of their own, are kind of agnostic to qualitative information. So, yeah, just something to think about for next time. But thank you all for watching. I hope you learned something. Feel free to write in the comments your own insights. I'll pin the best comment. And yeah, thank you all. See ya.